So I'll just let you see what it kind of looks like. This 92 inches in diameter. It's a very structurally sound steel container where you can reduce the atmospheric pressure to basically zero. We were at like 0.0001 torr, and 760 torr is normal atmospheric pressure. You need to get rid of all that air in there because you're shooting particles down an accelerator, and I need to make sure that they don't run into anything, and air particles are a thing. So I need to remove all the air particles. And inside of there, we have this structure. And what we've got here is, this was the last day that I was at Michigan State, and we had run our experiment, and we ran it twice and it failed. So we had a couple of hours left and didn't have anything else to do. So we ran the gold foil experiment, Rutherford's gold foil experiment. So this is right here, a piece of gold foil. And these things here, this, and this, those are things that can detect atoms and subatomic particles. So instead of sending somebody in there and having them look for little sparks of lighting up glow-in-the-dark paint, we had pieces of equipment that would actually determine the speed at which the object went through it and what its mass was. So then we can correctly identify exactly what the object was, whether it's going to be an alpha particle, a neutron, a beta particle, or a chip of something. And so we ran gold foil experiment just for the hell of it in the last couple of hours that we were there. It still worked just like Rutherford. All right, so the last thing in the set of notes I want to talk about are nuclear reactors. So they're not, it's not something that people are super excited about. If somebody said that they were going to build a nuclear power plant in Rowena, how would that go over? Not well, right? If they said that they were going to build a solar farm in Rowena, people would be like, hopefully I won't be able to see it, but they're not going to care about that. And what's the main impetus behind the, I don't want to say disgust, but the desire to not have one in your backyard? Most people are worried about what?
It melting down.
It melting down. All right. It's not happened in the US, but I mean, you can't go to Chernobyl. I mean, that word, the name of that town, Chernobyl, now has a connotation of nuclear meltdown and like stuff being very deadly, and you can't go anywhere near that. And that is true. But the idea that it's super dangerous is not really correct. The thing that I want us to absolutely know is, do you remember when we were talking about how at Oak Ridge, Tennessee, they purified the uranium-238 to turn it into uranium-235? And that most nuclear reactors run at 9% uranium-235. So usually it's about 0.000% of naturally occurring uranium. So if you just got a chunk of pitch blende, one out of every 1,000 uranium atoms would be the type that is useful. So they purify that to 9%, and that's what a commercial nuclear power plant runs on. The ones I was on for the Navy, those are at over 90%. And then for a nuclear bomb, it needs to be 99.999%. So literally purifying it 8 orders of magnitude more than normal. So it's not an easy thing to do. And if I don't get it that purified, if it's only 99.99%, it can't go nuclear. I can't actually have a nuclear explosion. I can have some bad things happen, and we'll talk about exactly what happened at Chernobyl, but I can't have a literal nuclear explosion. The best I can do is spread nuclear material all over the place from a regular conventional explosion. So that's what people are worried about. They don't want to see things, they don't want to see the environment messed up because a nuclear power plant went bad. Can we get rid of them? I mean, we've got nuclear power plants. We've finally just started bringing new nuclear power plants online, one in New York and a couple in Georgia. But why didn't we turn them all off when people got scared of them?
It's difficult to remove them.
They provide 20% of the electrical power in the United States. So imagine 1 out of every 5 people not having electricity. Like that's not a possibility, but nobody's going to go for that. So even though people didn't want them, they're there, and that's what we got, and so that's what we're using. Is there any good reasons to use nuclear power?
Is it efficient?
Yeah, it's very efficient. What else? Okay, lots of energy. What else? It doesn't do something. What is it?
CO2?
It doesn't produce any CO2. It's not a greenhouse gas emitting industry. So that was definitely something that gets talked about during presidential campaigns, like I'll reduce climate change by making more nuclear power plants. So that is definitely a thing. The reason that people got freaked out about it, and there was a certain period where they where this hype got very scary. Okay. Let's go with this one. Oh, it's probably going to be blurry, but we'll see. I'm into the new tab. That's terrible. All right, let's go with that one. Now, I don't for a moment believe any of you have watched this movie. No. Do you know who these people are?
You know, these. In order to move the change part. That's what I'm at.
So Jack Lemmon was top 5 actors from the 70s. Period. You might have seen him in Grumpy Old Men. That movie came out not 100 years ago, so possibly. Jane was a premier actress since the 60s, and she's still on Netflix. Like she's still doing stuff. And then Michael Douglas has made a bajillion movies, and you've probably seen a few of them. So we're literally talking about the 3 of the most famous actors in Hollywood when they make this movie. The premise of this movie is in New York City or New York State, they built a nuclear power plant. They cut corners in building the nuclear power plant in a way that the nuclear power plant is not safe. Jack Lemmon's character works for the company. He doesn't know that they cut corners, but he ends up finding out. Michael Douglas is a reporter, like an investigative reporter, and Jane Fonda is just like a puff piece reporter. And he converts her into being all heavy journalistic, and they find out that they've been using these cheap parts for the nuclear power plant. It's going to go bad. The term China syndrome is kind of ridiculous, but what it means is that the nuclear material in the core goes a little haywire, and it gets so hot it melts through the core. And it's so hot that it melts through the entire facility. And it's so hot it melts through the ground. It keeps melting through the core and then pops out on the other side of China. So can you give me the very obvious, that is stupid concept? It couldn't get to China. Like even if all that stuff happened, once it got to the core, that would be it. And then the idea that this runaway nuclear reaction would do something to the Earth, like break it in half, is utterly ridiculous because all that stuff is happening in the core right now anyway.
nuclear power. The inside temperature of Earth is hotter than the exterior of the sun. So like the middle of the Earth would be like, who cares? Don't care about this thing that just entered my moltenness. But people freaked out about it. They literally lost their minds, and nuclear power plants stopped being built after this movie came out. It's almost like movie came out, nobody applied for a new nuclear power plant. We were building the hell out of them in the 60s and the 70s because it was basically free, and the United States has a lot of uranium, so it's easy for us to put these together. They are very expensive capital investments, but once you build the facility, they last a very long time. They're all rated for about 25 years, and most of them have been running for more than 50. That's how well the plants were built. If I'm building a nuclear power plant as a private institution, I would build the hell out of it. I would make it run, because once it's running, it's minimal cost upkeep. You can't say the same thing for a coal fire plant or a gas fire, natural gas plant. You constantly have to feed fuel to it. You feed fuel to it, but it lasts 6 months to a year at a time, and it's inexpensive by comparison to constantly feed fuel into a nuclear or regular power plant, which also has trouble with maintenance and whatnot. So you spend a gross amount of money up front, and then it's just at that point a cash cow. It literally just makes money for you. So the idea that a company would cut corners and have the possibility of the thing being down for any reason whatsoever is utterly ridiculous. Capital investments are not things that people scoff at if they know the backside is all cash, which these things are. So yeah, this stopped nuclear power in the US, which is really weird because we had just come through an energy crisis with OPEC. And so the OPEC nations, mostly the Arab nations, decided to not sell us any oil because they were mad at us about doing stuff in their countries. And so we had just come through this, and yet we still decided to turn this off. Oregon had a nuclear power plant. It was in St. Helens. It was northwest of Portland. You could see it. And that thing got knocked down maybe 15 plus years ago. So yeah, we don't have any of these things in Oregon. Illinois is the state with the most. They went all in on it. So I put that Schoolhouse Rock thing up for us. We did the electrochem stuff, and so that's what this is trying to show you. This is these are pictures of the generators over at the dam. This is an axle for the generator. That's a person. So how much energy is it going to take to turn this thing? A lot. So we'll use the dam. We'll run water over the wheels or the turbines to get the thing to spin with the transmission. But what we're trying to do is get this huge thing to turn so we can create this electricity. So what is it that the nuclear power plant does? It does what all electrical generation plants that aren't solar plants do. And what that is they boil water. When it comes right down to it, unless I'm talking about a solar farm or a wind turbine, we're talking about boiling water. There isn't anything else to it. It's the nuclear power plants are the most expensive water boilers in the world. And that's it. If you could boil water, then you can make an electric plant. So people have made water boilers by using like a whole bunch of mirrors where they shine it down on stuff, and then it boils that water very rapidly, and then they use the steam to make everything turn. So all we're trying to do is boil water to steam. That steam is used to turn a turbine. That's the point. So why do we go through all this rigmarole of building a huge power plant for steam? So this is how it works. So I've got a uranium-235 atom. We already know that that's the only fissionable one. I need a neutron to go into it. When the neutron goes into it, it splits it into two smaller pieces. This varies. It could be cesium, rubidium, it could be barium and krypton, but they're relatively about the same size each time pairing up.
Obviously, all of the protons and neutrons have to add up when we do this. So the neutron goes in, turns this into uranium-236, splits them into these two fission products, and then it creates more neutrons, more neutrons, and those neutrons go off and they hit other uranium-235s that split, and then create more neutrons, and then they split other uranium-235s. So this moderator stuff, this is literally just purified water. So the neutrons themselves, they move so fast when they come out of the nucleus that I have to slow them down. And the way that we slow them down is using water. They come out of the nucleus and then they start smacking into water molecules. And that reduces their amount of kinetic energy to the point where they don't leave the core and run into the shielding immediately. And they'll actually hit another uranium-235. The moderator isn't doing a job, then the nuclear power plant does not work. It's just kind of nice that water worked. So remember when we were talking about the shielding, the gamma was 2 inches of lead. What was the shielding for water, or sorry, for neutrons? Water. 10 inches of water was a 10 thickness for it. So that's doing a dual purpose as far as being a moderator to slow those neutrons down. So as soon as these neutrons come flying out, they're going very fast. Then they run into some water molecules, lose their energy, and then they can run into another uranium-235, and then that can split. And so you can see that one turns into like 3, because this guy here is going to dish out 3 neutrons. So 1 turns to 3, 3 turns to 9, 9 turns to 27, and you can get out of control pretty fast. So initially, when you start the reactor up, that's what you're looking for. You're looking for an acceleration in neutron production, and that's the term for that is called supercritical. And then when you get to the point where this is the correct temperature, this is where I want it to be, then it's that's called critical. And that sounds kind of bad, but that's the term for it, critical. And what that means is every one of the uranium-235s that gets split, it will produce 3 neutrons, but only one of them will split another neutron. The other 2 neutrons are absorbed by shielding. So what you end up is this steady state system where every one disintegration of or fission of uranium-235 only fissions one other uranium-235. So you're at steady state power. So it takes a few hours to get yourself up to steady state power, depending on what's going on. If you're a dead reactor, needing coal, and then to get yourself back up to regular power, and then that thing will sit there. If we're talking about a conventional nuclear power plant for commercial use for electricity, 6 months, a year, nothing will happen. We'll just sit there and do that. People just wander around and check gauges, but nothing happens. It's obviously a job. It's super boring, but you want your job to be super boring. You don't want anything exciting to happen with a job like that.
On the ship, we used to turn the reactors on and off fast, so we could, check things during what might happen during combat. But under normal circumstances in the regular world, it just turns on and they just leave it running for as long as they possibly can until they run out of fuel, and then they swap the fuel out. And we talked about the fuel issue and the lack of a place to put the waste last class. So this process is fission. All right, so I've got the beginnings of talking about how this functions, but we're going to go through the whole thing so you kind of have an idea. So there's something called primary coolant. It's just regular water during normal operations. It's at a super high pressure, like 2,000 pounds, and the temp's 500 plus degrees. And the water performs 2 functions. It's the moderator, so it slows the neutrons down, and it's the thing that cools the reactor core. So without the water, the core temperature would go up very high, very rapidly, and it would get out of control and explode. Regular explosion, not nuclear explosion. So then there's 2 loops. You started a pump, you pump water through the core is cooled off. Then that hot water goes through something called the steam generator, where steam is generated. And as it goes through the steam generator, it's boiling water on the other side. And that water cools the primary coolant down. And so then you're back to the pump. And so again, it's just a loop. The secondary loop, same situation. This time it starts at a condenser, so it just got cold. It gets pumped into the bottom of the steam generator. It hits these tubes that are at like 500 degrees. So if like room temperature water hits 500-degree pipe, it immediately flashes into steam. And then that steam exits the steam generator, hits the turbine, spins the generator, and then that steam comes out of the backside of the turbine that's spent, like bathroom steam. And it hits a condenser who also has U-tubes, except the U-tubes are cold. And so then it takes the steam and turns it back into water, and then I start the cycle over again. So here's my diagram.
Fine, so, this thing here is the cooling tower. And this is the sort of iconical image. You're talking about a nuclear power plant. It's 20, 30, 40 stories tall. And there's nothing nuclear inside of that. It's literally just where water, I just got water inside of that. The nuclear power plant itself is sort of a dome looking structure, kind of close to it. And it's maybe 3 stories taller than its most. It's not very big. It could be a single story. It'd be totally fine. So, all of the nuclearness is inside of it. So the way this works is, here's my primary loop. Here's my secondary loop. Then there's also a condensing loop. And then there's a cooling. So I've got these 4 loops. So the interesting part about this is every single one of these loops is filled with water, but none of the waters in those different loops touch each other. So the primary cooling, all this water that's in here, can never come in contact with this water, which can never come in contact with this water, which can never come in contact with that water. If any one of these 4 loops were to break, then the whole plant gets turned off until they fix that thing. So it's the idea that primary cooling could leak some sort of nuclear material into the river that this is next to, or the ocean, or the cooling pond, or the lake, or whatever it is literally ridiculous. There would be so many alarms that would go off, and there wouldn't even be human control. Like if one of these alarms goes off, it turns itself off. I mean, obviously a person can do it too. They realize that before, but once it's reached this threshold, the thing just turns itself off. So I'm going to go through that whole loop stuff again. So here's the primary coolant water. Again, this is just water. It gets pumped through, and then it goes through this fuel assembly. The fuel assembly is the darker section are these rods of uranium-235. And the exterior of that is a particular alloy that will be able to withstand temperatures and the fact that nuclear reactions are happening. So the stuff that's radioactive is this dark stuff, and it is not in contact with the water. So when the nuclear reaction happens and uranium-235 spits out a neutron,
What we saw was it split. It splits, and then it runs into water, and then it splits on your other uranium-235s. So what's happening at the
core level is, let's say this uranium-235 in here breaks. It will shoot out neutrons, and they're going to hit uranium-235s in a different fuel rod. And so the fuel rods shoot out their neutrons, the water slows them down, they go into the neutrons go into the next fuel rod, and that's where another fission is going to occur. So the fissions are happening in between these, they're shooting neutrons at each other. And as that happens, again, the water gets hit. And so what is temperature a measure? And average kinetic energy of the system. The kinetic energy of the system is a measure of mass times velocity squared. The mass of the water isn't changing. So how do you change the temperature of the water? You increase its speed. But what would happen if a neutron were to fly out and run into a water molecule and the neutron's moving at like half the speed of light? The water molecule gets moved very fast, right? Imagine a cue ball getting shot out of a cannon at a pool table. What would happen to the pool balls? It would scatter like crazy. But the cue ball that got shot out of the cannon would slow down.
And if it hit enough of those cue balls, then it would be moving quite slow. And so that's what's happening. That's one thing that causes the water to heat up. The other part is, it's not just the neutrons that are coming out, it's also a lot of heat energy coming out of the nucleus. The nuclear material is turned into energy. So a lot of this is just simply joules of energy. And so the water comes into the bottom of the core at like 500 degrees and it leaves at like 550 degrees. So this 550 degree water goes into this steam generator, and this room temp water hits this pipe and it immediately flashes to steam, in the same way that if you had your stove top turned on all the way and you sprinkled some water on it, I mean, you wouldn't see any water droplets. It just turning into steam. So as this water is heating, as this primary coolant is heating up the secondary water, it goes through this and it cools down to like 500 degrees. So 550, 500, 550, 500, and it literally just loops for months or years, just sitting there looping. In the 4+ years I was on the aircraft carrier, we added less than a half a liter of water to the core. That was it. We never opened it up. We injection pumped a half liter, and actually we weren't injecting water, we were injecting sodium hydroxide, because the primary coolant, we want to make sure that the metal doesn't rust. Obviously, it's important. So we make sure that the pH is somewhere around 10. So that's several orders of magnitude away from acids. And so just as long as so we're constantly, just not constantly, but every few months we'll add like 20, 25 milliliters of a basic solution, just to make sure that the whole core thing stays basic. Inside of here, we have something called the control rod and another thing called the pressure. So I said that this pressure of this water is 2000 PSI. So obviously that's much higher than atmospheric pressure, 14.7 PSI. 14.7 PSI is when water would boil and turn into a gas. And here we are at 2000, and it's still a liquid. It needs to be a liquid. Gases are terrible at actually changing the temperature of stuff. If you walk outside in shorts and it's 50 degrees, you're cold. But what would happen to you if you jumped into 50-degree water in a pair of shorts? It would be really cold. So that's the situation. The gases can't extract the heat out of the core, and it's 1,000 times less efficient than liquid. So I need to make sure that this water stays liquefied. So I do that by using a pressurizer that keeps the whole thing at 2000 PSI. If I'm at 2000 PSI, water is still a liquid, even at 550 degrees. So I keep it pressurized. The control rods are things that go in between the fuel rods, and it's peculiar in that it will absorb neutrons and do absolutely nothing. So the control rods are an alloy, and the main alloy is made out of made out of hafnium. So hafnium's on the table. It's underneath titanium and zirconium. It's there at number 72. It's not a very common element. If we can mine it, it's like 5% hafnium, 95% zirconium, but you can't use zirconium control rod. So you have to be able to chemically remove the hafnium from zirconium. And that's not an easy process. That was actually developed in Albany, Oregon, to figure out how to separate those things out. So we make these control rods mostly out of hafnium and steel. And it's really weird. If there's a hafnium atom, there's a uranium-235 atom, and a neutron comes in, it will almost always go into the hafnium. And it just absorbs it and does nothing. It's a neutron sponge. So if you were to take these control rods and put them into the reactor core, the fission stops, because instead of the neutrons going and hitting another uranium, they run in and hit this hafnium and nothing happens. So that's how you would turn the reactor off. You can insert them slowly, which is the normal way. And inserting them slowly, it brings the power down, and it's a more controlled situation. But if something bad happens, the control rods are actually pushed up against the spring. You guys know what the springs look like in a truck or a car? They're called coils, actually. They're like the size of your thumb. So imagine a thumb-sized coil of wire into a spring. So as these control rods come out, and they're a couple of meters long, they go up and they compress one of these very heavy duty springs. And then there's a solenoid that goes in. And so if somebody wants to, they can flip the switch, the solenoid pops out and the springs rocket the control rods to the bottom of the core and the thing just turns off. There's a little backlash as far as some gases that are being created, but it's fine. It's not, it's the reactor is full. It won't like superheat. Okay, so that's how we control the process. We use these control rods, we pull them in or out depending on what we want the power to be. So let's look at the secondary loop. So the water comes in here like slightly cooler than room temp. It gets pumped up, it hits these pipes, it flashes into steam, the steam goes up, hits this turbine spins, the turbine is connected to an electrical generator, a giant axle with a bunch of wires and magnets around it, and electricity is generated. The steam that comes out of the backside of the turbine is like bathroom steam. So it hits this pipe is cold, and it turns this steam into liquid water, and it's called a condenser. So then that's what I have, water, steam, water, steam. This water in the secondary loop never touches the water in the primary loop. It's literally just in there, and we keep recirculating it over and over again. So how does the condenser get cold? I need this water to be super cold. So I pump the water through this pipe. And this is like, imagine, say, 40-story tall water slide. Big, huge pipe you could fit inside. And, going around it all the way down to the bottom of the corkscrew, except this is just filled with water and it's a steel pipe. From a river source or an ocean source or something like that, you take and you dump water down on top of the pipes. So let's say that you have a warm pipe and you dumped cold water on top of it. What would happen? The water would cool off in the pipe as it transfers its heat through the pipe to this water, and that water would turn into water vapor. And so when you're looking at one of these power plants and you see water, or you see a cloud coming out of the top of it, it's because it's a cloud. That's actually what it is. The water from the nearest source is literally just being dumped on top of these warm pipes. And dumping the water on top of those warm pipes cools the water inside the pipe, but the water that you dump on top of it turns into a cloud and floats away. So if you're driving by a nuclear power plant, you see this water coming out, or you see this cloud coming out of the top of the cooling tower, just look around, like, where's the water source? That cloud is that water source right there. So it's super easy if you're next to an ocean or next to a river or whatnot. It's next to a river can be problematic because when the water goes back in, it can't be too warm. If the water's too warm, then warm water doesn't have any oxygen in it. And so you could kill all the fish because you've taken all the oxygen out of water. So you gotta be careful with this. But really it's just a loop. So what I've got is this primary loop, all the water stays in there. The secondary loop, all the water stays in there. The condensing loop, all the water stays in there. And the cooling loop is just put into the atmosphere. So here, to get nuclear material into this river, the very first thing that would have to happen is the fuel rods would have to bust open. The fuel rod busts open, leaks out nuclear material. Then I have to break something in the steam generator. Then I have to break something in the condenser. And then I have to break something in the cooling tower. And I have to make sure all the pumps kept pumping. And a break in any one of those things turns stuff up. So the only way to get nuclear material into the adjacent water supply is to have something break everything all at the same time. So that's what happened in Fukushima. All of the pipes broke at the same time. The earthquake busted everything. You shouldn't build a nuclear power plant on earthquake fault. That's the point of that story. I mean, we obviously had two of those on the aircraft carrier that I was on, and we went through some ridiculously rough seas, like 100-foot waves. where our boat, I felt our boat going up and down. Usually you have no idea that you're on a boat because it's just so heavy. So massively immovable and didn't care. So they were hit with a very jarring earthquake. All the clearness is inside of here. It's a lead line concrete structure. So lead blocks for the gamma, the concrete blocks for any of the neutrons. And as long as you're on the other side of this wall, everything's fine. Definitely would not want to be inside of there. But, yeah, everything else would be, everything on the outside is totally fine. Do you have any questions?
I thought they used, graphite and something else as well.
Like, could possibly be a mixture along with the hafnium. That's a possibility. I'm sure there are other organizations that use different stuff. This is just what the US generally uses.
Graphite was the problem.
Graphite was a portion of the problem at Chernobyl.
It doesn't moderate.
It doesn't. The moderator there was sodium.
They had a big graphite tip on their control rods.
And the issue with graphite is at some point it just catches on fire like a charcoal would have. And nothing there is flammable unless you get like several thousand degrees and have plenty of oxygen, which there isn't inside of the fuel ventilator. But
What's the alloy surrounding the assembly?
mostly just steel that has the things that you typically, like when you make something out of steel, like this metal, there are going to be a lot of other metals inside of it, and you need to remove almost every single one of those metals. So on your homework, there was a question about cobalt. Cobalt 60 is a half-life, has a super high energy gamma with a 5.27 year half-life. Cobalt cannot be anywhere near a nuclear power plant because it will be turned into cobalt 60 when bombarded with neutrons, and then it will decay with this quite deadly gamma radiation. And so when you create the steel that the core is made out of, they have made sure to remove all of the cobalt. But really, it's just a steel structure with ridiculously thick walls kind of stuff.
I'm a little surprised, I guess it's that useful, like these everywhere steel.
Yeah.
I guess you can control how much of whatever.
I don't know if you guys remember me talking about. It's a good one. So what's the name of that? Okay, what's its chemical name?
Iron 3 oxide. Maybe
Iron 3 oxide. And what's the other one?
two
Yep.
something.
Yeah. Exactly.
It's the hide or whatever I think we get to.
If it's just a single element, it's always going to be iod. It's only not an iod if it's a polyatomic ion.
Okay, so remember why we said we had to say 3 and 2? Because otherwise you don't know how many irons and oxygens to put there, right? So it's Fe2O3 because if the charge on the iron is +3 and the charge on the oxygen is -2, then I least common multiple is 6. But for the other one, it's just one of each. So if somebody said, yeah, I got some iron oxide here, you would have to say what? Which one? There's at least 2 of them. So
This is regular rust, and you know the properties of regular rust. When the iron rusts, it turns orangey colored, and then that oxide flakes off. All right. Under special circumstances, when you allow iron to rust, you can, with oxygen, you can get it to rust iron 2 oxide. The major difference between these two things is this adheres deeply to the iron that it just rusted from. Does that make sense? So the problem with rust is when it rusts, it flakes off, exposing more iron, which can then rust, and then eventually you'll have a hole. But here, this iron rusts and then sticks hardcore to the underlying iron. So what can happen to that underlying iron? The answer is nothing. Why? It already rusted. The surface already has rust on it. It's just this rust sticks to the exterior. Have you seen those rhino liners that they have, the paint that they use on the inside of trucks, sometimes on the outside of trucks? I'm like, you could throw bricks and rocks and steel in there, it just doesn't care. That's what this is like. The inside is structurally sound, not able to be oxidized because it's already been oxidized. So these pipes, the interior of the core that's made out of steel, which you would imagine would rust at high temperatures and pressures, is coated with rust. All the pipes already have this done. This is an incredibly expensive process. It has to be very specific temperature conditions and atmospheric pressure conditions with oxygen for this to occur, to get this and not this. So making these pipes, making all of these fittings, the core itself, all of that stuff is, again, an expensive process. So when you build a nuclear power plant, it's a lot of money investment. But why do this? Because once it's built, I want it to run for 50 years and just keep paying me back. So they don't mess around. The requirements from the Nuclear Regulatory Commission were severe, and they should be. I mean, there are nuclear power plants that were built in the late 40s and early 50s that are still functioning. Why? Because they over-engineered everything because they were scared to death of a Chernobyl. Did not want a Chernobyl. Okay, so we've had an accident in the United States, right? Anybody know what that accident was? Well, there's one public accident. There's one very, very not public accident. Although there's a documentary about it. It's just not something that people normally have seen.
One can think of the one exactly, the other one we're testing a small reactor and
Yeah.
it melted down and then just shot straight to the sky.
Yeah, that's the one that people don't know about.
Let me guess this state on this Nevada, that's mine.
You're pretty far away. This is Pennsylvania.
This is called 3 Mile Islands. It's an island that's 3 miles long. It's got 4 operating nuclear power plants on it until the late 70s. And one of the nuclear power plants had a problem. So this is the only known instance, publicly acknowledged instance of a commercial nuclear power plant leaking nuclear material into the atmosphere. Okay, so what happened? It's an engineering problem called the double failure problem. So when you engineer something, you can engineer against a failure. Like completely engineer against a single failure. But to engineer against a double failure is kind of almost impossible, especially with a complex object. So imagine one part on your car going bad. There have probably been engineering issues to make sure that that doesn't kill you. But what if 2 things break at the same time? Well, there's so many parts on your car, like how would you have engineered it so you'd understand, so you could prevent problems when 2 things break? We don't even really care about cars that much. So what happened, there were 2 things that happened. This pressurizer has a relief valve on it in case the pressure gets too high. And inside this space, there's a temperature probe. The temperature probe broke and the valve leaked. So if the valve had leaked, then they would have known, because the internal, this is room temperature inside here, they would have known that it's never leaked before. But they did just touch it.
Oh, no, that's messed up. It's not wrong over here.
Like this is still full screen. Oh, the screen's just gone. Oh, that's cool. It's, looks like half, right?
Oh, that would be good. Classic maneuver, dude.
How do you turn it off and turn it back on?
Worst part is that it works. It's
Just the other day, after we found it in there, when Andrew came up here, I couldn't get this cord to work. And we were sitting in here and it did not work. And I went downstairs and got an IT guy, but I wanted to just tell him about it. He's like, well, let's go look at it. And he came in, he plugged in and it immediately worked. And I'm like, swear to God, that thing did not work 5 minutes ago. Okay, so had this thing leaked, the temperature probe would have said, hey, it's, you know, above room temperature in there. Somebody find out. And if it was really leaking and it, let's say, got to 100 degrees, then you're like, well, there's obviously a problem. They would have inserted the control rods, turned it off, and everything would have been fine. They would have had some maintenance to do on that valve, but nothing bad would have happened. But because it was leaking and the temperature probe did not indicate that there was a problem, nobody realized anything was going on. So what happened was this water was leaking out of here as steam. So the water level started to drop. It just kept dropping.
So what happens? Where's the point where it becomes problematic? Yeah, as soon as the fuel assembly, the level gets down to this fuel assembly level.
Well, what happened? And so now water isn't there to cool the fuel assembly. So instead of it being 550 degrees, it's 800 degrees, it's 1,000 degrees, it's 2,000 degrees. So what happens when to an object that is heated? Before that,
the molecules are moving faster.
it expands, right? You okay with that? Things that are heated expand, things that are cooled contract. Should have brought that brass ball and regardless. So now what I've got is an expanding reactor fuel assembly.
Well, the problem with having a expanding reactor fuel assembly is if I'm looking straight down at the core, it's got these holes. And it's got the fuel rods. So this right here is supposed to be, this is a hole that a control rod is supposed to go into. But if the fuel assembly starts heating, then this hole starts to get smaller, right? The whole thing is swelling, but it also swells inward. So when they finally realized that there was a problem and they went to turn the core off, they went to insert the control rods, and the hole is now too small for the control rod to go into. So they're like, oh crap. And they know that the control rods haven't gone in because there's a level indicator as to how far the control rod is into the core, and it doesn't go in at all. And so there's one emergency option. The emergency option is something nobody wants to use. There's another little pump right here. And it's got
A slurry of water with a bunch of boron, element number 5. So remember a little while ago, I said that if I've got a uranium atom and I've got a hafnium atom, a neutron will come over and hit the hafnium. If there's a boron atom there, it ignores everything and runs into the boron. The problem is the boron can't be used as a metal. It's not a metal, it's a non-metal. So I can't turn it into a rod. I can't impregnate it into a piece of metal correctly. So what it's used as is basically a last defense.
So I've got this large quantity, like a barrel of water filled with this slurry of barium. And if you push the button, the reactor won't ever work again. So you're like, how much trouble I'm gonna get in if I push this button? Well, at this point, they know the control rods can't go in, so they're certain that there's a problem with the fuel assembly temperature wise. And your options are, this keeps heating, keeps heating, keeps heating until all the water in here boils and the top pops off. Or you can do the boron injection pump and all the fission stops. All of the neutrons get absorbed by the boron. And so the problem is you can never get the boron out completely. The entire inside of the core will just have this boron laced into it. And so it's useless, can't be used for the nuclear power plant. So that thing has to get thrown away. So they push the button. It had gone on too long. The interior pressure here was about 4 atmospheres. This thing isn't rated for 4 atmospheres. Think about going down 120 feet in the ocean. How would that feel on your ears? Nice. So the interior of that, this is feeling for 120 feet of water pressure. So what they did is there's another valve up here and they released several thousand gallons of vapor water that absolutely did have some fission products in it, some uranium, some other waste products like cesium and rubidium that got released in the air. But it's a gas, so how much actual mass is there? Not a lot. So there was no discernible radiation signature produced by this. There wasn't like an increase in cancer anywhere around it or anywhere also. So the one bad thing about this is basically they've got a room filled with boron water. This whole facility is filled up with boron water, and it'll never work again. But the issue is it's still sitting there. They haven't fixed it. This is like 1979. They still haven't managed all of that water. And one of the main reasons is we still, as Americans, don't have a place to put the nuclear waste. It's supposed to go to Nevada, but we've never actually done that. So they don't have any place to put it. So we just have this defunct nuclear power plant with the boron laced core that's just sitting there doing nothing. So that's the one accident. So that movie comes out, right? Then this accident happens and everybody loses their mind. And we don't build another nuclear power plant for 30 years. Jane Fonda was right. Like that kind of garbage. All right, so I'm gonna here. So now we're going to talk about the one that Ben was mentioning. It's called the SL-1 reactor. The Navy has traditionally been the only institution that had access to nuclear power. The Air Force controls the nuclear missiles. Well, the Navy does too, but the Air Force controls the ones that are on the ground. And obviously in the bombers. But the only branch of the military that does anything with nuclear power has traditionally been the Navy. The Army was like, hey, we would like to have a portable nuclear power plant so we could like invade Korea and like set up shop wherever the hell we wanted, have as much power as we want. So they decided to steal some of the Navy's nuclear people and try to make their own reactor. So this thing would have to be super portable, like literally put it on the back of a truck and then take it someplace. So it's small, relatively speaking, small. It only has one control rod in it. The whole rest of the setup is the same. So one night it wasn't operating correctly. They're trying to do some testing on it. And for some crazy reason, they decided that the problem was that the control rod was stuck. So this guy stands on top of the core and grabs hold of the control rod. Okay. When the control rods are removed, they move at about a centimeter every 30 seconds. Okay, so obviously very slow. It takes a considerable amount of time to pull the rods out of a nuclear reactor to get the thing started. That's why I said it takes hours. So this guy is up there and he's like wrenching on the control rod and it won't move, it won't move, it won't move. And then it moves like a foot. So all of this uranium that's been around it has had all of its neutrons being absorbed, and now they're just not. So the power spike is about 1,000,000-fold. All of the neutrons in this area spontaneously fission, produce a ridiculous amount of heat. This thing's filled with water. The water flashes to steam. And if you're in an enclosed environment and there is a hole, the gas will come out of the hole. Well, the hole was the control rod. So the steam shot the control rod up into the ceiling with the guy in between the control rod and the ceiling. He was literally speared to the top of this facility in Idaho Falls, Idaho. Well, it's next to Idaho Falls in Idaho. He's literally hanging up there, dead, obviously, with a control rod through him, steam spewing up into his body. The guys in the control room go in to try to save him, don't know he's already dead. They succumb to the radiation. They send an ambulance. They go in. They succumb to the radiation. They send another ambulance. They don't go in because they realize something weird is going on. And so then they call out the cavalry. So several people died because somebody let the army mess with a nuclear power plant. This nuclear power plant they took all of this stuff, including the people and the ambulance, and they took it out into the middle of Idaho someplace on base and dug a very, very big hole and dumped all of it in it. Obviously, none of this is kosher. The military wasn't okay with it, but the base wanted to just get rid of all the evidence. Somebody found out about it, and they told us when we were in the Navy, and they wrote a documentary, had I don't know, something badly cinematography documentary on it, but it was still creepy as hell. If you like Google SL1 nuclear reactor documentary, you can see it, and it is creepy because the facility is still there and it's still at ridiculously high radiation levels. So nobody's let the army touch a nuclear power plant since then. As far as Chernobyl goes, the structure was a little bit different. One of the cool things about using water as a moderator, as the temperature goes up, its density goes down. So if I'm a fast neutron and I come out and I need to hit a moderator to slow down, but the water's not as dense, the chances of it hitting the water is less, which means the neutron is moving too fast to perform another fission, and it just runs into the shielding. So as temp goes up, our nuclear power plants have a tendency to cool themselves off nuclear wise because there's not as much moderator density. That didn't happen in this particular version of the Soviet plant in Chernobyl. So Chernobyl had slightly different control rods, but the main difference is the control rods were on a pulley system. Remember I said that the control rods come out slow and they go in slow, but we have a mechanism to fire them in at like gunshot speeds. They don't have that. So when they realized that there was a problem, they pushed the buttons and the control rods started to slowly go down into the core, and it was too late. So had they had the springs, maybe it would have worked, but they couldn't get the control rods to go in. They partially inserted themselves, and then the core swelled, the fuel assembly swelled, and then they couldn't go in anymore. And then the temp just kept building up, kept building up, kept building up. This thing is filled with sodium, metal, water, and some graphite from the control rods. This water boiled. The top of the reactor core literally popped off like an overheated pressure cooker in the kitchen. Knocked the roof of the shielding off and just exploded steam laced or uranium laced steam all over the place. So there's just all this fuel assembly stuff is just all over the place on ground. There was no nuclear explosion, no mushroom cloud, none of that. Literally, it was just a steam explosion that sprayed nuclear material all over the place. The way they got it out is they just dumped concrete. They had these concrete helicopters where they pick up a certain amount of concrete and just dumped it on top of it. Those guys almost all died. Pilots, because they were flying through a radioactive cloud and they were breathing all that stuff in. They still operate the other 3 nuclear power plants there. Like, even though it's kind of a ghost town, and it's kind of creepy, it's super creepy. I haven't watched the documentary, but I've seen older documentaries talking about how the 3 nuclear power plants are still there, how it was a prosperous society, because you had, people who were smart enough to do nuclear power there and trusted enough to do nuclear power there. And so they had influence. So they had an amusement park built there. They had nice parks built there, nice apartments built there. And now all that stuff is super creepy because nobody's been there for 30 years. And you can imagine what would happen to an amusement park with clowns and stuff if nothing happens to it for 30 years. Does anybody know what the only good benefit of what has happened there?
Is that why they added like the slamming mechanism, or was that beforehand?
The Navy had thought about that
Wow.
because if you have a nuclear power plant on a war vessel, you want to be able to turn the reactor off now. Like, I don't want to wait 20 minutes. I want it now. It needs to be turned off. So we had thought about that a long time ago. Any goodness come out of this? Do you guys know?
It was there were a bunch of rare species or something, about the extinct, something like that, and they started randomly popping up.
Yeah, the wildlife was like, yeah, we're getting cancer, but at least we're alive. So instead of them having their normal 12-year lifespan, they're having like a 10-year lifespan and dying of bad cancers, but they're procreating for those 10 years. And so the boar population that was almost decimated by the people who live there, it's flourishing. And you can't go hunt it, but it's not like you're going to hunt it and eat not going to turn it into bacon. It's laced with nuclear isotopes. Same situation with plants. A bunch of plants that basically had died because they cut everything down and then clear cut forested areas by just burning them down. All that stuff's growing back. So you have these 30-year-old forests that were decimated and now they're back. So there's a little bit of good stuff with it, and nobody will really live there. So all those plants and animals are sort of on like their own little nuclear sanctuary. What else with this? Any other questions? One other side note, I think interesting thing. There we go. That's good. Do this. Snip. You. There. So here's the deck of an aircraft carrier.
Anything odd about this? What's up with the steam? Heavy? That's what you about heavy. Why is there steam on the flight deck? Some water, friction from the tires. Oh, you said catapult. What's catapult? This is planes to take off on a shorter runway.
This jets can't take off
on an aircraft carrier without assistance. They afterburn, they fire it up. Obviously afterburn, so using this to take care of the jet wash, but it would just flip over the side. So the way that they get off, the way that they get up to, they're around 150 miles an hour, so they can come airborne because this jet has crappy wings. The only reason that this thing flies is because it goes so fast. So we did a couple of times have prop planes landed on us and take off. They don't need any assistance whatsoever. No, actually we had the Vikings. The Vikings didn't need any catapulting. They were propeller planes with much larger wings, so they could take off all of them. So this is a catapult, and you can see this little groove in here. This right here is a piece that attaches to the front of the plane on the front landing gear. And so you park the plane, they would attach it, you fire up the afterburners, and then this catapult would pull, it would literally pull and throw the plane off the front of the deck. So the way that it's not like an electrical thing, it's a giant torpedo looking piece of steel with a huge steam pocket behind it. So we have these huge tanks that we build up high pressure steam that push this thing to allow the plane to get up to speed. So these things move at like 150 miles an hour. And so to get the planes to launch, we would actually have to increase the temperature of the reactors, because normally it's around 525 degrees as the nominal average temperature of the reactor core. But these things need to get up to about 135, 140 degrees to make sure that the steam pressure is above 700 psi. And so we would occasionally get a call down to, we're going to start launching planes, get the reactor hotter so we can get the steam pressure up to the correct.
That's just water pulled out of the ocean or like that cooling.
Yeah. Yeah, but it's run through a six stage boiler unit that turns it into potable water, drinkable, cookable, showerable water. And then the water that goes into the secondary loop or the primary loop has to go through a deionizer. So the deionizer that I've got in lab, there's one that's like, I don't know, I'd guess 8 feet tall and bigger than I can put my arms around. And so all the water that we use for the secondary loop and the primary loop, and I told you in the primary loop, we put like half a liter of water in 4+ years. So that's not the issue. It's the secondary loop. So the secondary loop, that water.
There are lots of places in the secondary loop for like a little bit of steam to leak out. This is actually where we do the testing to see if there's any chlorides in the water. I don't know if you guys remember me talking to you about small pipes and steam leaks killing everybody in space. So we need to be able to check to make sure that there's no chlorides in this water here. So we use that. So yeah, I mean, we didn't ever change the deionizer 4+ years I was there, so it was totally fine. But that water that comes out of that, it's like the water that comes out of there. It's water. There's no other ions, no calcium, magnesium, sodium chloride, any of that stuff in there. It's just pure water.
More? Okay. So that's today, right? Yeah. If you guys are voting, you have to turn it in tomorrow.
Everybody,
Voting. Did you get a ballot?
I'm not. Check my mail. It's at my dad's.
You probably got a ballot. I mean, it's mostly just the primary, but for people who live in Hood River, it's important because they've got the pool bond on the issue. It's been kind of a hot topic. Everybody's property taxes will go up. Couple hundred to a couple $1,000s a year, depending on what your market value is. All right, so we've got, oh, we got plenty of time. All right. Yeah, we're a whole day ahead, so it doesn't even really matter. So we can just call it a day and go to lab. Remember, Monday is Memorial Day, so nobody's gonna be here. All right, the lab's right there. Next to Veronica. Scissors and tape.
Right, we're still ahead, because that one lap lasted longer than it should have.
Where it took us like 2 weeks.
We finished what we needed to in the one day, but it's just like. That's a week.
I should have just let you keep using the hand pump because that would have been funny.
We were going, we were gonna get everything out.
Do you think we would have added more of the